Callbacks in Windows have been used for some time to do call stack spoofing, evasion, shellcode execution, sleep timers, and many others. And many of the existing callbacks are very well known and have signatures for them. One of them that you might know and which is very popular is the enum Windows callback. In the enum Windows callback, the first parameter that we pass, which is passed through RCX within the assembly language, is usually the one that we pass as the function pointer, the user defined one. Now this, within this function's internal logic, is passed to the register R8, which is then subsequently passed to the stack and stored at arg10. Now if we track this down below, we can see that this is again passed to the register RAX and a call to this dispatch function happens, which I'll explain soon. So this research was to try and solve if it is possible to figure out a way that is automated and as much as possible that would result in callbacks that are previously undiscovered within the Windows subsystem. Now additionally, we also wanted to utilize a static method to find these callbacks without running the binary per se, using the framework MyASM, which allows us to use a bit of a graph theory and analysis to figure out the callbacks within a given DLL. Now, keeping this in mind, the entire point revolves around the fact that the callbacks could be identified because it has a unique signature attached to it. Now, this signature, which I'll explain again soon, is where we pass a function pointer like this and an indirect call happens. Now, since you have seen this, there is a less known callback within NTDLL that is called RTL run once, execute once. Now within this callback, we pass the particular parameter in the second argument, and that is in fact passed to RBP. And if we trace this down, we can see that RBP is passed to RAX and then a call to this dispatch function happens. Now this is very similar to the previous function that we saw, that is the enum Windows callback. Now since the signature is more or less the same, we can try to find an automated approach to find the simple case within a larger set of scenarios. So a fact to note here is that, as I mentioned, we want an indirect callback to happen, but within the Windows subsystem, indirect callbacks are completely protected by CFG, the control flow guard. So when CFG is enabled, we will need to accommodate that scenario within the binaries that we are targeting, and that could be modified as I showed you within this dispatch function. Now this dispatch function is the CFG protected function where RAX is a register where it takes a function pointer, the indirect call to the function, and within this, if we trace this down, we'll be able to see a standard jump to RAX. So if we are able to recognize this function within the larger binary, we'll be able to find if it can potentially support a callback opportunity. So we proceed to MyASM with the necessary details that it requires, and then we proceed to load the DLL into the framework for further analysis. As you can see, now this is the main function. Within this, we set up the necessary details and we proceed to prepare the file. I'll walk you through this code right now as a basic version. So we define a container for the particular DLL that we are taking in. We check if it is a DLL or not. We parse the export table and then store it in the form that MyASM understands, and then we add the symbols from the import tables so that we can avoid the unnecessary functions that we do not want to track that might be coming from another DLL, and then we turn the toggle on called isPrepared. Now once this part is done, we go through the start hunt function, which is the main core engine of this particular tool, where we store the final results within these two variables, and the entire point revolves around a very overview of a logic will be we go through every export function that is within the DLL that exists, and then we search if a call instruction exists, just like this. Now, if a call instruction exists within that, and we try to see if it is an indirect callback. Now, this is a direct callback, but we want to see if it supports an indirect callback. But then, since indirect callbacks are protected by CFG, we see if a call to a dispatch function exists within that particular function that we are trying to analyze. Now, if it does, we go ahead and try to see what is a parameter that is passed to this, and if that parameter could be traced back to one of the 4 arguments that we are passing to this function. Now, the problem with this is that sometimes the core logic of this tool fails. We use the use definition graph that is provided by MyASM, which can simplify the entire process of trying to find out if one of our arguments support within the callee of the dispatch function. But then sometimes this fails if there is a complicated reference or a dereferencing instruction within inside that. Now, when such cases happen, what we try to do is we try to see if a successor or a predecessor to that callback exists, wherever it exists. So, as I can show you over here, we use the usedef graph in order to check if it works well and good. If it doesn't, we try to see if a particular logic of the callee that is coming via an argument exists within one of the nodes that could be reachable in the current block where the dispatch function exists. So since the main block is reachable by the current block, we would be able to find that out even if the use definition graph fails. Now, there are more intricate scenarios and a lot of edge cases to avoid false positives within this entire tool, and all that is well explained within the blog. So please go and check out the blog. Now, here is a demo for the tool. The tool supports both a file and an entire folder where multiple files could be there. So in this case, I'll show you an entire folder. And the tool is also built using the main 2 frameworks called Click and Rich, which is used to provide a clean output and a more professional and simplified way to parse arguments within the command line. So this tool stores the final results within 2 major JSON files where all the results are stored within all DLL info about if an indirect callback existed, but then there's no potential callback opportunity. And then the second file, the hunt callbacks result, is a main file where the address and the function for each DLL where a potential callback exists is stored, and some DLLs where and the rest of DLLs where nothing is found. So with this particular tool, you can go ahead and proceed to find within any folder or DLL if a particular callback opportunity exists. Now, when we ran this tool, we were also able to uncover around 6,000 callbacks across 350 DLLs within the Windows subsystem, that is the System32 folder. Some of them, of course, might contain false positives, but we tried our best to avoid all the edge case scenarios that is possible. Now, there are many scope of improvement for this, and we encourage the user that is going to use this to try and find out a way to support indirect callbacks as well, which are not CFG protected. Now, that would additionally increase the number of callbacks that are previously undiscovered as well. So thank you for watching this, and yeah, have a good day.